Good morning, ma'am. This is Arka Organ from the Development A section. So today my topic is about the Wasserstein GANs for MR imaging from paid to unpaid training. Wasserstein GANs for MR imaging from paid to unpaid trainings. So before moving to challenges and MRI, first we have to know about GANs. Why GANs in MR imaging? As a background, magnetic resonance imaging MRI means magnetic resonance imaging. MRI is widely used because it has a high soft tissue construct, is no non-invasive, supports multiple modalites as a P1, P2, flare, PD. PD is nothing but proton density. However, MRI has challenges, just like long scale times, motion aircrafts, low resolution in fast scans, high cost of acquiring multiple modularities, just like as a long scale time and data needs, it means high quality MR imaging traditionally require lengthy scan times and fully sampled case-based data, impacting patient comfort and hospital efficiency. Paid data scarcity in the sense supervised training methods demand meticulously matched, undersampled, and fully sampled data, which is often unavailable in clinical settings, limiting their application. Need for unpaired solutions. There is a critical need for advanced methods that can achieve high quality MRI reconstructions without relying on scarce paid ground through images, enabling faster scans and reduced patient burden, and its goals are to use deep learning to enhance resolution, which is a super resolution, denoise MRI, convert one modularity to another, reconstruct the missing or corrupted data. So first, what is a GAN? A generative adverse serial network has two models, generator and discriminator. Generator means it takes noise RNA input image and generates a fake image. And discriminator is nothing but tries to distinguish real versus fake. They play a min-max game. Here is about an introduction to Wasserstein's GANs, the generator's roles, the discriminators, tasks, input image quality, Wasserstein disciplines, enhanced stability. Coming to generator's role, the generator image can create synthetic images aiming to replicate the characteristics of real MR images. And coming to discriminator task, the discriminator acts as a critic learning to distinguish between the generator's synthetic images and actual real MR images. Coming to improved image quality, ultimately WGANs deliver significantly better image quality, which is crucial for diagnostic accuracy in medical imaging applications. Wasserstein distance WGANs utilize the Wasserstein distance is superior metric for measuring the difference between distributions, leading to more stable training. Enhanced stability. This approach reduces common GAN issues like mode collapse, ensuring the generator produces a diverse and high quality range of images. Here the paired LT is a paired training with WGANs in MRI, generator design, discriminator function, supervised learning, data limitation. Under generator design, the generator is an unrolled neural network explicitly combining conventional layers with data consistency layers to produce realistic images. Under discriminator, function, a multi-layer conventional neural network acts as a critic scoring the realism of generated images to guide the generator's learning. Supervised learning, paired training leverages matched undersampled inputs alongside fully sampled ground truth labels, enabling highly accurate supervised reconstructions. Data limitations, while producing high quality reconstructions, this method is significantly limited by the inherent scarcity of perfectly paired datasets in clinical patients. So, before moving, why Wasserstein GAN? So, the key idea about it is that instead of measuring how much two distributions overlap, WGAN measures how far apart they are. Wasserstein distance. In one pile of stand is equals to real images, another pile is equal to generated images. Distance is equals to minimum cost to transfer one pile into the other. It is better because it has smooth gradients, stable training, meaningful loss curve, better convergence for medical images. And there are some changes like discriminator is a critic, no sigmoid output, enforce constraints, weight clipping, or gradient penalty. And what is a paired data? It means nothing but each input image has a perfectly aligned ground truth output. Just like if the input is low res MRI, then the output will be high res MRI. If the input is T1 MRI, then the output will be corresponding T2 MRI. The objective of paired WGAN is generator learns a direct mapping. Loss function combines Wasserstein adversarial loss, pixel-wise loss. Pixel-wise loss is nothing but L1 by L2. And its some applications are like super resolution MRI, artifact removal, modularity translations. And its limitations are paired data sets are very hard to collect, require, and it requires same patient, same position, same time. It is expensive and impractical in real hospitals. Coming to the lead to unpaired training. There are independent datasets overcoming scarcity, distribution, alignment. In independent datasets, unpaired training utilizes undersampled MR images from one dataset and high quality images from a separate and related dataset, overcoming scarcity. This innovative approach removes the need for exact input label pairs, effectively overcoming the critical data scarcity challenge in MRI. Distribution alignment. Adversarial training aligns the distributions of reconstructed images with those of real images, leveraging the distance for robustness. The unpaired WGAN framework contains artifact supervision, quality evaluation, diagnostic validation, radiologistic approval. Under artifact supervision, the generator excels at placing artifacts in under sampled reconstructions even without direct paired supervision, enhancing the image clarity. Under quality evaluation, the discriminator evaluates reconstruction quality by comparing it against a diverse pool of compared high quality images, ensuring high standards. Diagnostic validation. This framework enables diagnostic quality reconstructions which have been validated on real world MRI datasets demonstrate its clinical utility. Radiologist approval. Expert radiologists have consistently rated unpaired WGAN reconstructions as superior to those produced by traditional paired text pixel-wise loss methods and endorsing its effectiveness. And why unpaired training is needed. In reality, hospitals have independent collections, no pixel to pixel correspondence, different scanners, protocols, and patients. So we need unpaired learning. Unpaired training with Wasserstein GANs. Its idea is to learn mapping without direct pairs. Just like example, if a set A has a T1 MR images and set B has a T2 MR images, and there is no alignment in between them, then the solution is only cycle consistency. Then it generates two, just as A to B and B to A. Two critics will be as DA and D. Cycle consistency loss. If we translate that, we should get the original image as A raises to G of A and G of A raises to F of G of A, which is equal to A. And B raises to F of B and F of B raises to G of F of B, which is equal to B. Here it is about complementary advantages of a cycle GAN and unpaired MRI. The optimal transport driving stable training, high resolution reconstructions, broad applicability. Under optimal transport driven, the optimal transport driven cycle consistence GAN represents a significant advance, utilizing a single generator discriminator pair for efficient learning. Stable training, it is derived from advanced optimal transport theory incorporating a penalized least squares cost functions to ensure highly stable and reliable training. OT cycle GANs excel at reconstructing high-resolution MR images from accelerated case-based data previously without requiring matches references images. Under broad applicability, this versatile framework supports both single and multi-coil acquisition, significantly broadening its potential for diverse clinical application. And in clinical impact and future directions, has a total 4 points, that is reduced scan times, just like unpaid WGANs drastically reduce MRI scan duration, enhancing patient comfort and significantly improving hospital throughput. Multi-domain synthesis, they facilitate multi-domain MRI synthesis and cross-modality image translation, opening avenues for converting MR images to CT and vice versa. Enhanced accuracy, future integration of attention mechanism and transfer learning promise for even more accurate images, refining diagnostic capabilities. Robust clinical deployment. Ongoing research aims to extend these advancements to 3D imaging and larger datasets, ensuring robust, widespread clinical development. And under visual comparison, paired versus unpaired reconstructions, it observes the striking differences in image quality, artifact reductions, and detail preservation between paired and unpaired reconstruction methods. This comparison clearly highlights significantly improvements in diagnostic features achieved with unpaired training data, demonstrating its practical feasibility and growing acceptance among radiologists. At last, in conclusion, transforming MRI versus unpaired with unpaired Wasserstein plans in overcoming data limitations. It has unpaired adversarial training successfully addresses critical data scarcity challenges in MRI reconstructions, opening new possibilities. In stable and high quality synthesis, GANs deliver stable, high quality image synthesis, which is absolutely essential for reliable clinical applications. New frontiers in imaging. This paradigm shift users in new frontiers for accelerated, flexible, and multi-domain MRI imaging, revolutioning medical diagnostics. In revolutionary workflows, it embraces unpaired GAN framework to fundamentally transform and revolutionary medical image workflow. Thank you.